And it's a pleasure to announce the next speaker. It's Professor Funaki from University of Tokyo, and he's going to talk about scaling limits for a dynamic model of 2D Young diagrams.
Okay, so first of all, I would like to thank the organizers, Professor Brezeniak and also Professor Lechner. Thank you very much for the invitation. So, as Professor Lechner announced, the title of my talk is Scaling Limits for a Dynamic Model of two-dimensional Young diagrams. Actually, the motivation of this talk comes from the paper by Bershik, which appeared in '96. He discussed the scaling limit for the Young diagrams here. So, Young diagrams is just a collection of unit squares. So, like so just the unit squares, and you piling up unit squares, you get some shapes. Then, but in my talk, I just write this shape upside down because it is better to think about. In the first quadrant, I follow the idea of the Bershik. Therefore, the Young diagrams have this shape. So this is x-axis and y-axis. Then you have some. So I just write down the shape of the boundary. So the shape of the surface of the to the Young diagrams is just a step function with values, integer valued step functions, and jumps occurs at the integers values. That is and also this is a decreasing non-increasing function. And Bershik gave several statistics. That means he considered random Young diagrams. So, for simplicity, so the simplest statistics is just you fix the area of Young diagrams to be n. So you have n unit squares. Then the simplest randomness is just a uniform probability measures for all possible, for the set of the all possible Young diagrams. Then he discussed what happens as the area n goes to infinity. So of course the size becomes large. Therefore this becomes very big. So he just considered the scaling. So he scaled down by, so if area is n square, then he scaled down x-axis by n and also y-axis by n. Then the area is kept to be 1. So then he observed some shapes, limit shapes appears in the limit. So this is a kind of a Lagrange number because he considered random Young diagrams. Then the limit shape is deterministic and given some concrete form. So that is called a Bershik curve. And the Bershik curve depends on the statistics, of course. So this is a uniform case. But if you consider another randomness, then you get another shape of the curves. So my motivation. So this is considered as a static case. So the Young diagrams appears in the several subjects of mathematics, for instance, representational theory, and also say combinatorics, or in this case maybe Bershik considered the connection with the statistical mechanics, I think. And from the point of view of the statistical mechanics, this is a static theory. Static theory means the equilibrium theory. So the motivation of my talk is to establish the corresponding dynamical theory. So I want to introduce some dynamics, so random evolution of the Young diagrams. Then what happens for this dynamics? Then I will explain in the first, so the plan of my talk is in the first section, I will introduce 2D Young diagram more precisely and introduce statics or randomness for these Young diagrams in the first part. Then in the second part, I will explain again what is the scaling limits obtained by Belsik. And then in the third part, I will explain what kind of dynamics we can associate for these Young diagrams. Then actually we can take some scaling limit for this dynamics, which is called the hydrodynamic limit. And then we get a nonlinear PD of parabolic type. Then actually what we can show for this nonlinear PD, as time t goes to infinity, we can recover this Belsik curve. Because the Belsik curve is for the static case. Therefore, the dynamic, if the dynamic goes to infinity, then you can recover. So that is what I want to talk about in section 4. Then I will give the outline of the proof for this hydrodynamic limit. Then in the 6th section, I want to explain the dynamic fluctuation. That is so you get a nonlinear PD and you get some movement of the curves. Then you study the fluctuation around the limit curves. Then you get actually some stochastic PD, which is the subject of this workshop, I think. So I will explain what is a SPDE. Actually, the fluctuation for this Young diagrams is studied by Pittel, and he derived, so Russian mathematician. So he studied the fluctuation theory, but in this case, slightly different. Therefore, I don't recover his result from this SPD result. But anyway, I want to explain what kind of SPD we will get in the limit. And then in the final section, I want to explain what kind of problem I want to study afterward. So, yeah, I didn't say, but this is a joint work with Makiko Sasada, who is one of my graduate students in University of Tokyo. So Young diagrams originally appears just a partition of integers. So you give integer n, then you consider the partition of n. So that means, so I put also 0, but you want to give a partition for n. That means sum of integers, pi. I equal from 1 to maybe k varies, but anyway. Then I arrange pi from bigger one. The biggest one is called p1, and the second one is p2, and then you just arrange in this way. So for each partition of n, yeah, pn. So script pn is the set of all partitions of n. And qn is also the partition of n, but I assume pi all different. So p1 is strictly bigger than p2 and so on. So I denote by q, but anyway. So we give the constraint that these are not equal. In that case, we call such partition by Qn. And we can associate a Young diagram from these partitions by just piling up this one. So one P1 is here. Then the function 1 over the interval from 0 to pi is just this function, this step function. Then P2 is here. Then you pile up the next one with height 1. So already this is height 1 on this stick. You continue this way. Then you get the Young diagrams. So I call this Young diagram by psi p, and instead of x, I call this variable by u. Just next slide. In the next slide, I give some examples. P1 is here, P2 is there, P3, P4, P3 and P4 are same. Just I piling up this just stick with side length P1 and height 1. Then the next side length P2, height 1. Just you pile up these sticks. Then you finally get Young diagrams. As I said before, the usual people write the upside down, but I just want to get the Bell-shaped curve realized. I want to realize Bell-shaped curve in the first quadrant. Therefore, I write in this way. For Q, so this in this case P3 equal P4, but for Q, Pi are not equal. These are not equal. Therefore, say P3 and Q4 are slightly different. So I just remove one square over there. Maybe I don't have anything. So the area of this Young diagrams is 22. This one, so you see just one square I remove. Therefore, the area is 21. Just something like that. So this is the definition of the Young diagrams. Then I give some ensemble or the probability for this space of the Young diagrams. So first one, which I already explained, is a uniform probability measure on Pn. So Pn is the Young diagrams with area n. So this is a Pn is of course a finite set. Therefore, you can consider uniform probability measure on this space. That is called the uniform statistics. And mu Rn, that is a restricted uniform statistic. That means a uniform probability measure on Qn. That means height. So actually. So this situation is not allowed in Qn. So this is called the height difference indeed. So height difference should be 1 in the Qn case anyway. That is restricted uniform statistics, which I call mu Rn. Yeah, mostly we consider these two probabilities. Of course, Bell-shaped considered several other statistics. For example, Planck error measure, which is quite related to representation theory, but that is much more difficult in this sense. So I just consider these two measures, these two cases. These are from the statistical physics point of view, these are canonical ensembles. These are called the canonical ensembles because the area is fixed. But the grand canonical ensembles is just the superposition of these measures. The grand canonical ensembles, just for instance, for U statistics, just for if P belongs to Pn, the probability is the same because n of P, just n of P was just the area of the Young diagram P. Therefore, mu, so first I give epsilon, which is a parameter from 0 to 1. Then I define mu u epsilon P by this formula. Z u epsilon is a normalization constant. But just you should observe that the conditional probability of this one for on Pn is a uniform probability measure, which I defined already because n of P is a constant on Pn. So this is just a superposition of the grand canonical ensembles, a superposition of the canonical ensembles as usual in the statistical mechanics. And also I define grand canonical restricted uniform measure in this way, in a similar way. We are concerned with these 4 probability measures on the set of the Young diagrams, 2-dimensional Young diagrams. Then I want to introduce the result by Belsik first. Then I want to move to the dynamic problems. Thank you very much. Okay. So actually, I want to discuss the problem for the grand canonical ensembles. Then, so this is a grand canonical measure on the set of the 2D Young diagrams. Then I want to decide the parameter epsilon in such a way that the averaged area of the Young diagrams becomes n square. So I denote small n, but capital N. So I want to decide the parameter epsilon in such a way that the averaged area of the Young diagrams becomes n square for the uniform case and also restricted uniform case. Restricted uniform means that just height difference is just 1, always 1. Then we can see that the epsilon nu behaves like this: 1 minus alpha over n plus next to the term. Actually, you can show this. You can derive this constant by using the so-called Hardy-Ramanujan asymptotics of the. So Hardy and Ramanujan gave the asymptotic behavior of the number of the 2D Young diagrams with area n. So this behaves some exponential to something. That is the Hardy-Ramanujan formula. By using such kind of formula, you can actually find what is the first order term as n goes to infinity. So that you can actually compute the first order constant is pi over square root 2. And in the restricted case, the first constant is pi over square root 12. Then Belsik introduced the scaling for the Young diagrams. So in this case, the area is n square, but he scaled down. So this becomes very big. Therefore, he scaled down this diagram in such a way that the average area becomes 1. To do this, you have to multiply or divide by n the vertical direction, and also for the horizontal direction, you just shrink this shape by n. So then this, so psi p is just the surface of the Young diagrams. Then the scaled down surface of the Young diagrams is denoted by psi tilde pn, which is defined in this way. Then by definition, the area, expected area of these Young diagrams is always 1. Then Belsik studied what happens as n goes to infinity for these functions. This is still random. This is random function, of course. But then what he proved in his paper is that Loblaws number holds under these measures. Then this converges to some function which is defined in this way, but this is not so easy to see. But this psi u so uniform statistics u is actually 1 minus 1 over alpha times log 1 minus e to the minus alpha u. So if you write this y, then that is equivalent that e to the minus alpha u plus e to the minus alpha y equal 1. So maybe it is easier to see this formula instead of this formula. Just you put the alpha here and minus alpha, and then instead of log, you have an exponential e to the. So therefore, this is symmetric in y and u. So of course, the Belsik curve is symmetric under this 40-degree line. Just symmetric because, of course, the measure is symmetric. Therefore, the limit should be symmetric. But for the restricted case, slightly different. So in the restricted case, I think it should be minus something here. Maybe minus here, I think. So in restricted case, of course, the derivative of the curve should be smaller than 1 by definition. Therefore, curve becomes like this. Indeed, that is not symmetric in the xy. So actually, the shape of the Bell-shaped curve in the limit, in the uniform case, is like this, and the restricted case like this. But of course, the area of this below this red line, red curves, is always 1. This area is always 1. But in this case, this is symmetric under this 40-degree line. So I go back again. So this is a random 2D Young diagrams, but I consider only the surface of it, and I consider uniform statistics. So P denotes uniform statistics, uniform randomness. Then the limit is a Bell-shaped curve defined this way, and for the restricted case, the limit is given by this formula, or by this formula. So this is the result by Bell-shaped. And I consider the grand canonical case, but the canonical ensemble, under the canonical ensemble, you have the same result. That is also his result. Now, I want to introduce the dynamics for these Young diagrams. So which is invariant under these measures? So I consider grand canonical ensemble. Mu, say, mu mu epsilon u, but epsilon depends on capital N, or mu r restricted uniform epsilon. So I consider grand canonical ensemble like this. Then so that each square at the surface may disappear, eliminated with the rate 1, or created with rate epsilon. Then we can show that such dynamics, random dynamics, has these measures as invariant measures. Just simple computation, indeed, I cannot. So the dynamics is very simple. So this maybe this square may be eliminated. Sorry. So this creates. So of course here you cannot create any squares because the Young diagram should be decreasing function. But all possible positions at all possible positions, this square may be created with rate 1, but eliminated with rate epsilon. So epsilon is smaller than 1. So the creation rate is slightly smaller than 1. Therefore, this is weakly asymmetric in a sense. And also at the boundary, we consider there are infinitely many squares. Therefore, you can create at the boundary. You may think there are infinitely many squares. Therefore, you can always create and also eliminate at the boundary. It is always allowed to eliminate. If this situation, you can eliminate. Okay, so this is the dynamics which has the grand canonical ensemble as its invariant measure. And it is better to think about this dynamics as a particle systems indeed. So we just look at the height difference. So here, height difference is 1. Then you put one particle here. Here, the height difference is 1. Therefore, you put one particle. Here, height difference is 0, so there is no particle here. Here, height difference is 2, then you put the two particles. So in this way, you can identify each Young diagram with particles system. Then this creation means here is a height difference 1, so that means one particle is sitting on this side. After creation, height difference becomes 0, but height difference here becomes 1. That means that this particle jumps to the right with rate epsilon. And also elimination, under elimination, this particle jumps to the left with rate 1. So in this sense, for the particle system, jump rate is weakly symmetric because the epsilon is almost 1, but not equal to 1. So almost 1. In this sense, this is a weakly asymmetric, actually zero range process. And yeah.
If you take epsilon greater than 1, the dynamics
no.
exists.
Yeah, dynamics is, yes,
What
yes.
about invariant measures?
I think, you cannot come back to the picture of the Young diagrams, but you can think about, of course, such kind of dynamics for the particle system, other particle system. But I think Young diagrams just increase or something like that, maybe. I'm not sure. So. Okay. Then, in the uniform case, there may be two particles, but for restricted case, height difference always 1. Therefore, only one particle can sit down for the restricted case. That is actually the exclusion process. So, just what I explained is written here. So we have originally pi, the variables are pi. Then we consider the height difference, the Young diagrams, define the particle number, xi x, that is particle numbers sitting at side x is denoted by xi x for the uniform static case, and restricted static case, I denote it by eta x. Then eta x is always 0 or 1. Xi x is non-negative integers. So restricted uniform case, only one, at most one particle can sit down. The uniform case, maybe two particles or more can sit down at one site at the same time. So as I explained already, for the uniform static case, weakly asymmetric zero range process, and also there is some boundary condition at 0 because you may put infinite many particles there. Maybe I write in this way at 0, site 0, there are infinite many particles. Also, as a restricted uniform case, I consider as if there are infinite many particles at site 0. So in this case, the jump rate to the right is given by epsilon, which is slightly less than 1, but which is behaves like epsilon behaves like as I wrote by Hardy-Ramanujan formula alpha. Alpha is square root by 6, something like that. Then jump rate to the left is given 1. Yeah, of course, you can take this one and then epsilon inverse. That is essentially the same, but I just normalize this jump rate to the 1. And the same for the restricted uniform case, but only one particle can sit down at each site. That is the only difference compared with this case. Then, so we have a particle system, or we are actually interested in the dynamics of the Young diagrams, or the Young dynamics of the Young diagrams. But this is defined through the particle systems picture. Then we define the scaling for this dynamics in this way. So this is essentially the scaling due to Vershik in the space. But at the same time, I introduce the diffusive scaling in time. So as Vershik did, we shrink down to the vertical direction and also horizontal direction by n. At the same time, we speed up the time as a diffusive, so diffusive scaling. So n square comes in to the time. New scaling comes in. Then I define the scaled motion of the Young diagrams in this way. And in the similar way, we can define in the district uniform case. So what is the limit for these two objects? So what we can show is the following. So our main theorem, first main theorem is this one. So if the initially this converges to something, then for T positive, this scaled motion, random motion of Young diagrams converges to something. So this is random motion, but the limit is actually non-random. The limit is the time evolution of the limit curve is governed by this nonlinear PD. This is slightly complicated, but so the time derivative of this curve is given by, so psi prime is the derivative in the u space variables. So this is a second order parabolic PD. And alpha appears here. So alpha is first order term in this weak asymmetry. So yeah. So I assume that this is C1 indeed, and C1 and non actually decreasing. So the derivative is negative because it is natural to consider that initially this curve is a decreasing function C1. Then more precisely saying, the classical solution of this equation is unique. Yeah. Which is smooth. C1. Yeah.
C1.
Yeah. So this scaled Young, the motion of the scaled Young diagrams converges to the solution, unique classical solution of this equation, and this is unique. Therefore, the limit is deterministic. So this is a law of large numbers result. Actually, the idea is a hydrodynamic limit. So it's a local equilibrium. Then you take a local ergodicity. You should prove, and then you take a local average, something like that. Then you get this kind of equation. And as I said at the beginning of my talk, as time t goes to infinity in this equation, the solution converges to the solution of this right-hand side becomes to be 0. Then you can check easily that the Vershik curve satisfies this 0, the equation that the right-hand side to be 0. And also the such solution is unique. Therefore, for every initial data, you start this dynamics. Then in the limit, this scaled dynamics of the 2D Young diagrams converge to actually the Vershik curve as t goes to infinity. You can characterize in this way the derivation of the Vershik curves in the uniform statistic case. So this is another derivation of the, in a sense, another derivation of the Vershik curves in this setting, dynamical derivation in a sense. And also the restricted uniform case, we can show some similar results, but the equation in the limit equation is different, of course. The limit equation is given by this formula. Maybe this is much simpler, but with the boundary conditions here, derivative, so this is Neumann type, but the derivative is always minus 1/2. So in this case, so in the uniform statistic case, the curve diverges at 0, but in the restricted uniform case, the curve has some definite value at 0. And the boundary condition is given by this formula. In the last case, we don't need any boundary condition indeed. So just plus infinity and 0. Under these conditions, the solution is unique. But in this case, we need these two boundary conditions. Yeah, maybe, but it's infinity. And also in this case, the Bell-shaped curve is a stationary solution of this equation. So the Bell-shaped curve satisfies this is equal to 0. You can just plug in the formula, the Bell-shaped curve, then just you take it, compute the second derivative, something, then you can observe very easily it satisfies this equation, in fact. So the outline of the proof. So this is indeed the hydrodynamic limit. But for the uniform case, indeed, this is, so you have a Young diagram here, and you put the particles at the height differences. So these are height particles. And then it is better to rotate this by 45 degree, then project to the x-axis. That is written here. So you rotate this Young diagram by 45 degree. Then you just project on the x-axis. Therefore, this empty side comes here. And then you have one particle here. Then this is empty, one particle, empty, particle, and empty, 3 empty sides, and particle side, and something like this. This transformation is actually called the Russian transformation, and this is Bell-shaped or Kerov, and several people always consider this kind of transformation indeed to study the scaling limit of this. So we also consider such kind of transformation for the particle system. Then the nice is this, so the particles number is always at most 1 after transformation. But before transformation, of course, the 2 particles can sit down at the same site, but of course, just rotate 45 degree and then project, then only 1 particle can sit down at most. Then you can transform the so-called zero range, weakly asymmetric zero range process into weakly asymmetric simple exclusion. Exclusion means only 1 particle can sit down, occupy each site. So it's slightly easier to study exclusion processes rather than the zero range process. Then, in fact, for the zero range, exclusion processes, maybe I don't have enough time to explain. So just I write the generator more precisely for the zero range process, but maybe I just keep it. And then for the exclusion processes, hydrodynamic limit was studied by Geltner a long time ago, more than 20 years ago. And he proved for the weakly asymmetric exclusion process, empirical measure of such process is converged to the solution of viscous Vargas equation. Before the famous Go-Papanicolaou-Baladan's result appears, he proved already this kind of result. So we just rely on his result, Then this Russian transform formation is microscopic, but macroscopically we have some corresponding transformation. Then we just transform this viscous Vargas equation under this Russian transformation. Then you get a nonlinear PDE, which I already wrote down in my theorem. So the proof is rather not so difficult because we have this result, and also this transformation idea of the transformation is clear. Therefore, maybe it's not so difficult in this sense. And also the boundary condition disappears under this Russian transformation. Therefore, you don't need to worry about anything about the boundary condition. But for the restricted case, we have to worry about the boundary condition indeed. So restricted uniform case, we already have a weakly asymmetric simple exclusion process. Only one particle can sit down, can occupy each site, because the height difference is limited, at most one in this case. So I just switched to the restricted uniform case. Then we have to worry about the boundary condition. We cannot use this Russian transformation. It is not so useful. Therefore, you have to work with this original process. Then you have to worry about what is the boundary condition, indeed. But the equation itself is already studied in a sense, by Geltner. Therefore, it's not so difficult. So what we have to show, we have to think about is just what is the limit boundary condition in this case. Then, yeah, actually, we will get Vargas equation, viscous Vargas equation in the limit. Therefore, what Geltner considered is just introduce the Hopf-Kohl transformation at microscopic level. Of course, at the macroscopic level, if you introduce the Hopf-Kohl transformation, then the Vargas equation can be transformed into a linear equation. So, but he also introduced at the microscopic level. Then, actually, then he proved, but Geltner's case on the whole line. But in our case, we have to worry about what is the boundary condition for this model. Only what we have to worry about is this boundary condition. So yeah, anyway, just the idea is just we introduce the Hopf-Kohl transformation at the microscopic level, and then prove the hydrodynamic limit for the transformed processes. Then linear equation appear in the limit, and we have to show what is the boundary, like this mixed type boundary condition appears in the limit. And once you get this, then you just go back by taking the inverse Hopf-Kohl transformation. Then you get the limit, and you get theorem 3. So the only point is how you can prove the boundary condition like this. But there is a way by shown by Ewing, Leibovitz, Spohn almost 20 years ago, but this is rather complicated. But in our model, we can skip. So they proved the so-called the one block estimate at the boundary, but we can skip this kind of complicated argument indeed. Much more simple argument. Much more simple argument proves this kind of estimate for the simple exclusion process, weakly asymmetric simple exclusion process. At the boundary site, the time average becomes constant, converges to one half in the probability sense. We can prove this kind of boundary condition of the particle system in a rather simple way. Maybe I don't have the time, but this is a point-wise ergodic theory. In the Leibovitz, Leibovitz Spohn case, they have to take average also in space, but we don't need to take average in space. In this case, much more precise asymptotic at single site can be shown. But anyway, this gives us the precise or the appropriate boundary condition for our limit equation for the scaled 2D Young diagrams. Then now I want to move to the dynamic fluctuation problem. This is actually still not precisely studied. So claim means not theorem. So it's just still some heuristic argument comes in. But maybe this should be true. So we proved the scaled 2D Young diagrams with uniform statistics converge to some motion of curves governed by nonlinear PD. Therefore, we consider its fluctuation. So this converges to this. Therefore, we multiply square root n. So it's like a central limit theorem. Then we define the fluctuation of the random dynamics, scaled dynamics of 2D Young diagrams around the limit in this way. And also for the restricted uniform case, we define psi q n in a similar way. Then what is the limit? So yeah, actually we again use this Gaussian transformation. First we project, rotate and project, then we compute what is the fluctuation in after rotation, something like that. Then we come back to the original one. Then that gives the SPDE like this. So this is a parabolic SPDE, a heat equation type SPD, but linear. Actually, this is Ornstein-Steinbeck. This is Ornstein-Steinbeck type SPD. The coefficient depends on t and u, but this is the derivative, space derivative of this one. So rho tu is a negative minus of the space derivative of this Belsky curve. If t goes to infinity, this is a Belsky curve. But so some coefficient comes in, but otherwise this is Ornstein-Steinbeck type process. And also the noise term has some coefficient, which is explicitly given by the solution of the nonlinear PD. And W dot is a space-time white noise on this space. Maybe we need some boundary condition, but that is not specified at this moment. At zero, maybe we need some boundary condition, but this is slightly heuristic, so at this moment I don't know. For the restricted uniform case, that is much more clear. And in the restricted uniform case, the limit, this is more well studied already. So the limit is the solution of this Ornstein-Steinbeck process with coefficient rho. But the rho is the derivative minus of the derivative in space of the solution of the nonlinear PDE, but with the boundary condition, Neumann boundary condition at 0. So yeah, usually people compute such kind of SPDE assuming the so-called the Boltzmann-Gibbs principle, but we can prove without using Boltzmann-Gibbs principle. Boltzmann-Gibbs principle means for the hydrodynamic limit, so local equilibrium, so some nonlinear term is averaged by the Gibbs state, something like that. But the Boltzmann-Gibbs principle gives the next to the term should be something, the derivative of this average, something like that. So once you assume, you also get the same result. Therefore, I'm almost sure this is true answer. But this is still not theorem, but just claim. Maybe we should work more carefully.
How about invariant measure for psi u?
Psi u, this one I think. Psi u, I don't know. Actually, psi r, so maybe first going. I just let me. Yeah, I think so. Yes. For the invariant measure for this psi r can be computed explicitly indeed. So as Professor Daprato gave a talk, in our case, the covariance operator is given by this formula for this equation. Then the invariant measure is just Gaussian, mean zero Gaussian with covariance operator given by this, defined on this L2 space with Neumann boundary condition at 0. Of course, as t goes to, so invariant measure means t goes to infinity. Therefore, rho is just a derivative of the Berish curve. Yeah, in fact, Pittel studies static fluctuation and actually canonical measure, not a grand canonical measure. We are studying about for the grand canonical measure. Therefore, at the low Bragg number level, grand canonical and canonical measures is the same, but I don't check very carefully, but I think it should be different from what Pittel get. Pittel also proved the central limit theorem for the 2D Young diagrams, and he computed also the covariance operator in his paper. But maybe it's not same as what he got in his paper. And that is still not studied. So as Yura asked, but for this equation, it's more complicated. So at this moment, I don't know what is the invariant measure. It should be Gaussian and it should be computable. But I don't.
What boundary condition is here?
Yeah, the boundary condition is not clear at this moment. Yeah, that is another point. So at this moment, I haven't. We don't. Yeah, maybe we can do, but I don't know at this moment. So finally, the future plan. So I am just now doing the surface diffusion case. That is a conservative dynamics. So in my talk today, each unit square may appear with rate epsilon and disappear with rate 1. But so that is correspond to the grand canonical measure. But the canonical measure means the size or the area of the Young diagrams is kept to the n. So that means this square may be eliminated, but at the same time, this goes somewhere. Then at the same time, this square is created. At the same time, then area is kept under the dynamics. That means that this atom, so this is the atom in the statistical mechanics. This moves around, then this goes to some stable position. Or this comes to this way, maybe here, is created. So this is called the surface diffusion, because on the surface of these Young diagrams, atoms move around and find the natural position to stick. That is so-called the surface diffusion. So I am now studying carefully what happens in the limit for this model. The limit should be fourth order equation, indeed. And actually very, very difficult indeed. So I cannot go to the final position at this moment. So we extend the Varadant method for the non-gradient case. Non-gradient case means, I cannot explain, but the non-gradient case means the sum under the hydrodynamic limit. You have always some so n square. So you time change to t to n square t. Then you get always a divergence factor. But in our case, so Varadhan actually invented some very nice technique to delete such divergent factor. So, but in my case also n to the power 4, it's much difficult. So I have to eliminate this effect. but I have some hope to do this, so this is what I'm doing. So this is a two-dimensional case, and also much more interesting case is the 3D case. Then actually the limit theorem corresponding to what Basic did in 2D case is studied by Sarp, Kenyon, and Oknikov already. So they proved some variational principle for the limit shape. So I have some hope, and actually I can construct the dynamics which correspond to this, what they studied. So this is a weakly asymmetric simple dimer process on a honeycomb lattice. Indeed, I think I have no time to explain. But anyway, in the 3D case, there is a surface, and instead of the curve, the surface moves around, and maybe as t goes to infinity, then we get what these people studied in the limit. That is my hope, but I'm not so sure I can really do this. Okay, maybe my time is almost up. Thank you very much for your attention.
Yeah, thank you very much. Are there any questions, comments? There have been already some questions during the talk.
So those are questions which you have written down both in deterministic one and the stochastic one. So can you solve them independently in a sense? So you only know that the limits satisfy the equation, or can they be solved?
Yeah. So in the fluctuation case, the coefficient contains the solution of the nonlinear PD already. Therefore, maybe first you have to solve this nonlinear PD first. Then you can solve the SPD.
But so you can find through the existence and uniqueness of that.
For the SPD, I don't actually.
No, but even for the deterministic one, you can.
You can. Classical solution is already unique.
Any more questions or comments? I think in the 3D case, there's also work, at least in preparation, by Borodin, because he gave a talk in Bielefeld. But I don't know whether this is already on archive or something. I don't know the exact status, but maybe this should be.
Yeah. But in this case, actually, we need some information for the Gibbs measure indeed. But the one-dimensional distribution for this surface or the gradient of surface is known by these people. But the joint distribution, something like that is not known. So that makes much difficult.
But that's a major problem.
Yeah.
There is no other questions, then let us thank the speaker again.